Hello, could you hear me? May I start? Hi everyone. If I can start, please let me know. Okay, I can hear nothing from the organizer. Anyone could me say if you can? Okay. Okay, I'm checking the messages. I will be wait. Hi,
Good morning.
hi, good morning. I can
Am I audible to you?
hello, I can hear you. Well,
Good morning, Lucia ma'am. Am I audible to you?
yes, I can hear you. I am ready.
Okay. A very warm good morning to one and all present over here. Today we are going to start with our first session. Formally, our welcome today is start the afternoon session. But even though the official inauguration of the conference is planned of the evening, we are about to start the first session of day one now. I'm glad to welcome all the dignitaries and the participants for the today's session. The today's first session will be going to handle by Dr. Lucia ma'am from Mexico. So now I handed over mic to Dr. K.K. Ramendran sir.
Okay, thank you for the presentation. Let me share the presentation for you. Okay, let's start. I hope you can see the presentation. Okay, well, the presentation is about electrosorption, characterization of activated carbon as potential as electroabsorbent. I'm Lucia Alvarado. Yes, I am from Mexico. Mexico, in a province of Guanajuato. I work at the university in the Department of Mines, Metallurgy, Geology, in the engineering division. And for me, it's a pleasure to stay today here with you in the 6th Biennial International Conference. Okay, let's start about what I am doing in the research. Well, like the outline, we're going to talk about the introduction, some environment impacts, methods of treatment of effluents, activate carbon, electrosorption, and some results about the electrochemical characterization of carbon conclusions and some reference. Well, this talk is about what happened with we have some effluents with metals. Metals, metals are so important in our life just now for technology, for any transport, any buildings, and many ways. So we need to take the metals, but in this process, yes, absolutely, is difficult to have some process that could be maybe better to don't not impact to the environment. In the environmental, we have sometimes these metals are present in the some effluents and come to the lakes, to the rivers, and in one or another way, these metals will be into our organisms, into the doing some impact in the land, in our body too. So what happened with we work with this kind of effluents? We need to check what is any good procediment, any good methodology to remove it, to recovery, and work for any method that could be good and recover these metals and avoid the impacts, environmental impacts. So, what are the different methods for treatment? For example, typically we have heard about chemical precipitation. We can add any chemical. We can get this metal in a solid now, but we have this metal in solid, yes, but we generate another residue, another pollutant maybe, and we need to dispose this solid too. Another method, for example, is adsorption. We can use any material to absorb these metals. Or yes, for example, ion exchange. Ion exchange is so popular, we can use columns. We columns for the effluents going through the column, and then can exchange this metal for another metal or another ion that could be less dangerous, for example. Another methodology is about, for example, electrodialysis. In electrodialysis, we can use a system, electrochemical system, that use membranes. When we use this methodology, we apply an electrical field, and the electrical field do that metals that is in aqueous systems could be moved following this potential or this field. So this methodology is very good to use it, but the problem sometimes is that the membranes could be blocked if we cannot control the pH, for example. And we can use this kind of methodology, but if you use the membranes and that the membranes are blocked, so the resistance in the system will be increasing. So that is bad, because you can get more and more resistance, and so you can use more and more energy with a low efficiency. The another could be the osmosis. The osmosis is good to remove some pollutants, but for example, mainly it's about the size of this pollutant. So it's a little bit expensive about the use of pressure. Ever always when you use any methodology and this needs, for example, use of pressure, you can spend more money for that. Okay. So the another one, for example, in electrochemical field is electroionization. I have worked with these two. And the problem with this technology just now is that it's so similar to electrodialysis, and one problem is the membranes too, but another one is that this technology use a like a mix, is electrodialysis and ion exchange in the same system, and you need to check so good the pH, the change of pH, because you can generate solids into the system, and the solids into the system will be not good for the system, because we need that all the species be in aqueous state. And finally, the electrosorption, that is the technology that in this time I want to discuss. This technology work with the apply of the electrical potential, but is so low, is around 1 volt. This is why the people is studying more and more about this technology. And another one is that you cannot use membranes in the system. What is of this kind of technology? These are from the online, but it's just for show what is the structure for the activate carbon. The activate carbon, I think that everyone can remember it look, but if you can see that in the microscope and you can check what is the area, the activated carbon could be get areas about the 500 or 3,000 square meters per gram. Is a huge earth. So this is a potentially of this material. How can I use this material? Okay. A typical electroabsorption reactor is an electrochemical reactor when we can use this like two electrodes, and between the electrons you can put the solution or do the recycling the solution. And if you apply a very low electrical field, you can get this polarization about the electrodes, and then the species with any charge. For example, for metals, usually the charge is positive. This charge will be to the electrodes. We can use so low potential, I said like 1 volt, because we need just a very low potential, because we need that just this species go to the electrode and be absorbed. We don't need a Faraday process. We don't need change of or transfer of charge. We just need that the species go to the electrode and then go to the surface and stay together. This is why the potentiality of this kind of methodology. Why? Because in the another system, electrochemical system, we need any barriers like membranes, but in this one, no. In this one, the potentiality is just in the electrode. If you can give a huge area into the electrode, you can capture more and more ions. And this is why if you apply a very low potential, so you can get just this charge, these species that could be absorbed into the electrode. And when you apply this potential and the solution is recycling into the system, so in the time you will get a purification of your effluent. And in the second step, you can recycle less water or less fluent, and then stop with the polarization, so you can get that this charge go back. And then this is kind of methodology that permits you can treat big or huge volumes of any effluent, contaminated, polluted effluent, and then you can get a small volume with these species. It's like electrodialysis in one way, but you cannot use membranes. Just the potentiality is in the area of the electrodes. This is why it's important to generate better electrodes with a huge areas. In this case, I'm going to show some results about some characterization of the electrodes using activated carbon to check the potentiality of this material. And we have worked with chromium-3. We have one solution of chloride chromium and this concentration, and we have used activated carbon from natural stones from fruits and some mixes of that. This was the mixed, was from stones, and then I have put here one diagram about the species of the chromium. Why is important? When we have different pH into the solution, we change the species of in this case of the chromium, right? So it's important because the charge is different for each different species, and that it means, for example, this is negative, this is positive, and this is good too. You can make a good engineering in your reactor, and you can know how you can expect about the absorption too, because the sides of the carbon is like have some charge into the surface. So this is important because it will be not the same have two charges or have three, because that means three sides or two sides. Okay. We have checked about the potential of the substrate, in this case different mixtures of activated carbon. This is the range of the pH that we can use it. When you have a set of potential that is positive, that it means that the surface will be positive. So what it means, if you use this material before pH 3, you're going to attract a negative species. This is why you need to check what is the setup potential of the substrate of the surface, because you can check in what range of pH you can work. In this way, we're going to work with chromium 3 that in let me see, with this species, the second one. So we need that the surface have a set of potential negative in this way. This way we can work in this range or pH. Okay, and the experimental setup was about we have used activated carbon supported on graphite bar. We have used electrode like reference, calomel, and counter electrode a graphite bar. We get some results. We have calculated the specific capacitance like this equation, and then we get some results for cycle voltammetry. When we have checked this cyclic voltammetry, we get these results. The more important, this experiment is the first one, for example, and we get this information and then calculate the second one. In the potentiostat, we can get this and then we calculate, and this became in these and other parameters. So when we have checked the material, we use different scan rate to check what will be the facility to some ions going to the surface and how the time affect this. When you apply a slowly scan rate, you can give the time to the ions going and move to the surface very well. And how you can see in this second one about the specific capacitance diagram, we can see how in 1 millivolt per second we can have a bigger values about Faradays per gram in capacity of this material. Is around 40 for here and for here in 30. Why is different the value? Why is not the same and the opposite? It's because the species. When you work for the positive or anodic potentials, more positive, you're going to cut negative species. When you work in the opposite side, you're going to have your electrode like cathode, so you're going to attract a positive species because your cathode is negative, right? So the difference into the capacitance is because the species that is attracted. So the another important thing is that the species are different in size, and the size of the pores of the material become important, and this important too about how is the size of each kind of of ion. For example, for chromium-3, it's reported that the radio is 62 picometers, and for chloride, that will be the opposite ion that we have in the solution is 3 times, is bigger 3 times. So this is the difference why is not symmetry. There are not symmetry between this graph. And well, this is for a date olive mixture, and we can reach maybe around 50 Farads per gram. For another substrate, we can find that is less, is almost 20, and for this way is almost the same. The shape is different in each kind of substrate, and this is because the difference of pores too, and the way that is captured this kind of ions. And for the last one, I'm sorry. Okay. Okay. The next one, for example, the capacity is less. It's almost 4 times that the first one. This report has been done because in France we have some colleagues that they usually try to get new materials and have huge areas. We can, for example, in some reference, if you have 30 Farads per gram, it is a very good value to use like adsorbent. So if we can analyze these results, we can say that if we start for this kind of species, that implies that we have two in charge. That implies two Farads in charge capacity. Then this is some calculate. If you need, for example, remove all the chromium from 1 liter of solution, in base of this calculus will be necessary this quantity of carbon. So this is an example that we can imagine how is the capacity of the carbon. It's good, and it's so good, and we know, for example, this is why we use it in the filters for the water to remove pollutants, right? But now we are trying to get systems with huge area and capped some pollutants, in this case metallic, and then could put the opposite process and then take out the metal but in less volume. And in these results, well, this mixture was the best results for us. As conclusions, well, for talking about some methodology, there are not just one that will be the better, but you need to check what is the condition of your reflect. And well, I think that is better is think about how we can get a system, closed systems, to avoid the impacts. And well, you can see what is now the electrosurgeon and what is the advantage about that. And well, this is all. Thank you. Thank you for your attention.
Okay, thank you, Professor Lucia, for that
Thank
enlightening
you very much.
session. So it is maybe we are very sorry for that initial technical slack.
No worries.
Okay, okay. Then how are you? Hope you are fine.
Okay, yes, thank you.
Yeah. So after a long time, we are meeting online.
No, it's okay. Thank
All
you.
right, all right, all right. So, dear audience, she is speaking from the just opposite part of the globe, and we are here, in fact, with a very good morning. But she is, in fact, at 9:30, maybe 10 o'clock there at Mexico. So this is, in
Okay.
fact, COVID has given us this opportunity to talk from such a distance without much hassles. Of course, for the initial trouble what we had, I'm really sorry, the organizers, because our all net internet facility is down there in the college. So now we are hosting from outside. So sorry once again, sorry for that interruptions initially. So again, we in fact missed that good introduction that I want to make here on behalf of Professor Lucia. In fact, she is, she is Lucia Alvarado. She is an expert in electrochemical separation system, such as electrolysis, electroionization, and green chemistry. She has contributed in the areas of test and characterization of new carbon materials and nanomaterials. Her main research is designing treatment systems to remove metallic ion from wastewater and producing pure water. Currently, her position is full professor in the Department of Mining Engineering, Metallurgy, and Geology at University of Guanajuato in Mexico. She is an active member in the International Society of Electrochemistry and has been acting as a reviewer for many international journals and conferences. So I thank you very much for this enlightening session, very dear Dr. Lucia.
Thank you very much for this invitation, and I send you a lot of blessings to you. Thank you for all your assistance. I hope hear from you soon. Thank you.
Thank you very much. I hope you will meet somewhere after the COVID-19 threat, somewhere in the world, somewhere in the conference.
Thank you.
Thank you very much.
അടുത്ത ടോപ്പിന് അതില്ലേ സുമേഷ്
Okay. Yes, hello.
have the first keynote speech for the session one by Professor Dr. Sumesh P. Tampi from IIT, Department of Chemical Engineering from IIT Madras. His research interests include soft and active matter, surfaces and interfaces, complex fluids, fluctuating hydrodynamics. He is one of our distinguished alumni of Government Engineering College, Thrissur, and I am happy to welcome Professor Sumesh P. Tampi to deliver the keynote speech. Over to you, sir.
Hello.
Audible?
Okay, great.
Okay, yeah, okay, may we please
Yeah.
start?
I'll just share the screen first.
Yeah, please.
Yeah, so you can see my screen now?
Yes, it is loading. Yeah, it is fine.
Okay, yeah, thank you. So let me start by thanking Manilal and other organizers for the invitation. Uh, so I have chosen to talk about a research topic on heat transfer. I understand that we have a diverse audience today from chemical, mechanical, metallurgy, and so on. And heat transfer is a common theme, I think, among all these disciplines. And I hope that you will be therefore able to, follow and get something out of it. One thing I would prefer is if you have doubts, clarifications, please do stop me, ask, or put it in the chat box, and I would be happy to address them if I know. So this particular topic I started working on just 6 to 8 months back, and so I'm as new as many of you might be, so it will be worth discussing few points. So with that, let me start. So let me tell you a little bit about why we started doing this problem. Okay, so this started because polymers or plastics, right? In layman terms, is something that everybody uses in lots of applications. And one problem with the material is the low mechanical strength or low Young's modulus associated with it. And one way to improve the mechanical strength of this plastic or polymers is to disperse some solid particles in it. So that's what you see on the left hand side here. If the blue is the polymer, and then you disperse particles, preferably nanoparticles, okay, so that you can actually gain or improve the mechanical properties of the material. So but it's not very easy to disperse the particles, and one of the ways in which or there are several ways, and then when people were trying to do this, what was found is that several times the particles would be dispersed, okay, like in a random fashion. I hope you can see my cursor, right? So here, as you see, the black are the particles and the white is the polymer background, and essentially the particles get dispersed all over. Or sometimes it may happen that the particles align, like in this neat arrays. Okay, so and depending upon the way the particles get dispersed, you get a variety of properties for the material. So then the question arises: how does one, when does the particles align? How does one control the alignment of the particle? Similar structures also form even if you disperse simple particles in a fluid like water. So here what you have is water, okay, the bluish background on which you have these particles, and when you freeze them, what you find is that these particles align like this array. Okay, and that is and then they're separated by this grains in ice. So aligning of particles is very common during the phase transition. So on the case that I have talked about in the left, it's basically a polymer melt that is getting crystallized. On the right hand side, it's simple water that is getting frozen. So in both cases you have a phase transition, and during the phase transition the nanoparticles or the particles essentially move and then align or form arrays. So the question then is, can we actually control these arrays? Can we predict where do they go? Okay, so that's where the problem actually started. Now, so then people started doing controlled experiments. So let me tell you one such controlled experiment that was done. So here you have a polymer filament. So when I say filament, it's sufficiently thick. It's a sample, what you see on the red color. Okay. And then there is this geometry. Okay. Something that you can move, what is also shown with the circle. So this is a heating element. And then what happens is that when you move this heating element from, let's say, top to bottom, the polymer melts. But when the heating element moves away, the polymer again crystallizes. So if you think about how the temperature profile would be, it will be cool, or let's say at the top, it gets heated and then it cools once again. So that's exactly the temperature profile shown here in this picture, where on the x-axis you have the position measured from the top to the bottom, and then on the y-axis is the temperature, and you can see that the temperature increases, reaches a maximum and goes down. Okay, so wherever there is this maximum, that corresponds to the melt phase, and on either side you will have the cool phases. And what was observed was that when you basically do this heating part, and then when you pull this heating element, then very interesting structures form. So I'm not sure how much this figure is visible. What happens is that polymer molecules essentially align, forming certain structures. So this is details of the structure, but the point that I'm trying to drive is that by having a heat source which is moving, you are actually melting and then recrystallizing the polymer, and during that process you are able to control the structure of the polymer. And it turns out that it's these structures that are actually responsible for moving the nanoparticles that are dispersed. So the question that we had is that, if you are moving the heating element with a particular velocity, what happens to the melting region? How much of the polymer is going to melt, or how much of the ice is going to melt? How fast does that melting region move? Okay, will the region that's left behind by the heating element, will they get frozen, and so on? So as you may imagine, all of them depends upon the heat transfer characteristics, the temperature profile in the sample. So with this background in mind, what we did is we basically defined a simple problem, and what I'm going to talk about today is essentially the solution of that problem. And the problem is defined as this: that you have a 1D domain. Okay, let's say this part, the solid object, and this solid object, let's say some part is melt and the other part is solid, and this red line that I have drawn is an indication of a heat source, meaning that you are essentially heating that region. And when you are heating that region, you do expect that the material around it's going to melt, and that's why I have shown it with this gray color, which is that of the melt. And this red line is not static, but we let it move to the right hand side. That means that the more and more solid is going to melt because of this moving heat source. Okay, and the question that we are asking is, if I move this heating source with a particular velocity v, can I predict what is the temperature profile in the melt? Can I predict how far is this melt solid interface going to be? So these are the two questions that we have. Okay, and I'm going to tell you how does one find this now. Okay, so as you may have realized that this is nothing but a simple heat transfer problem. Okay, you want to calculate the temperature, so that means you're going to solve the heat balance. But the only complication comes, there are two complications. One is that you have a source that is moving and you need to account for that. And the second is that there exists a phase transition between the melt and the solid, okay, and which itself is moving. Okay, so you need to account for all these aspects into the model. So how does one do that? So before doing a moving heat source problem, I will actually do a simpler one, and the simpler one being that I have a heat source, but I don't move the heat source. What do I mean by that? Is that if there is this entire domain on the left hand side of the boundary, okay, here I will say that I suddenly change the temperature. Let's say I suddenly raise the temperature here, and I'll maintain that temperature, and I'll see what does the velocity, what does the temperature profile look like, and how quick this interface move from when I go from left to right. So this is what I'm going to address first. Now this is a very classical problem. Okay, this is known as Stefan problem, and this is being done like in early 1900s, but I think it's good to take you through that because it gives us a lot of insight. So as I said, we have now this is a system that we have. You have the melt, and on the right hand side you have the solid, okay, and there is an interface, and then on the left side you have a different temperature because of which the solid continues to melt, and this blue line which indicates the melt solid interface continues to move to the right. Okay, to know the temperature, we definitely have to solve the unsteady heat balance. So that all of you are familiar with. On the left hand side, it tells me how does the temperature change with respect to time. And on the right hand side is basically telling you how much, whatever be the heat that is getting conducted is reasonable for the change in the temperature. And how fast that conduction happens depends upon the thermal diffusivity. So this is the heat balance. Now this is true everywhere in this domain, okay, we're both in the melt domain and in the solid domain, but except at the interface. And what is different about the interface? At the interface, you have the solid that is melting. That means that you are essentially utilizing the heat available to give it as the latent heat, or there is a latent heat of melting associated with it, and you need to account for that. Okay, and that is typically done by using the so-called Stefan boundary condition. So Stefan boundary condition is what I have written down below here. This says that whatever be the conductive flux in the solid and whatever be the conductive flux in the liquid, if they are same, that means that there is no latent heat that's getting used up. But if there is a difference, that is basically nothing but how much is the latent heat that is used for the solid to melt. And of course, using that, the boundary is going to move, and therefore you can actually have a velocity of the interface. So this heat balance, the local heat balance that is done at the interface, is telling you that the difference in conductive flux should be related to the latent heat, which I denoted with delta H, and the velocity of the interface. You can imagine that if delta H, the latent heat, is large, the velocity will be small. Okay, so if this is assumed to be a constant. On the other hand, if latent heat is small, the velocity has to be large so that the interface moves much faster. So that is the standard Stefan boundary condition. One could solve the system, okay, and the solution I'll come to, but let me show you what the solution already looks like. So you initially start by saying that, let's say, everywhere the temperature is 0, and suddenly you raise the temperature at the left edge. So that's what I have done. So here on the x-axis I have the distance, on y-axis I have the temperature, and then I start by saying that at z equal to 0, the left boundary, I have a temperature 1, but at everywhere otherwise it is 0. So you actually have a step profile. Okay, soon the solid will start melting and the temperature will change, and that change is shown by this various lines here. So as time proceeds, you will see that initially you will see this as a blue profile and then it changes to the red profile. So this is how the temperature changes in the system. Okay, and somewhere here will be the solid melt boundary which will keep moving. Now, this is a simple problem for which you can actually calculate an analytical solution, and the analytical solution is given here. Okay, you can use one of the standard methods. This is nothing but just a PDE with two different variables, okay, an unsteady heat equation. So, which I am sure many of you would have encountered in the textbooks. So, you have temperature, okay, which is a function of distance and time in the melt phase, is given by some constant. So, lambda is some constant that comes up, and then the most important thing is it comes out to be a function which is basically an error function of z minus zl divided by root of t. Okay, so z minus zl is nothing but the distance from the left boundary, and then t is the time. So the error function is a function of z by root t. Okay, now this is very important because in the entire temperature profile, you don't see Z and T separated. Okay, there exists only one combination of Z by root T that comes into the entire equation. So that means that it doesn't matter what value of Z or T you are talking about, all that matters is the value of Z by root T. Okay, so a particular z at a different time of t could also, you can have the same thing coming up at a different z and at another instant of time t. Okay, so such profiles are called self-similar profiles, which means that the temperature profile is now not dependent upon the two variables separately. It depends upon a single variable which is defined as z by root t. Okay, so the profile will change always. Okay, so the temperature would not remain constant anywhere. Let's say if you look at a temperature at a particular point, it will change as if it has reached at another instant in time. Okay, so those profiles are called self-similar profile, and the temperature profile in the melt basically comes out to be a self-similar profile. Okay, where this z by root t is called the similarity variable. So you can solve that. The other thing is this Z0 minus ZL, which is nothing but the distance between the interface and the left boundary. Okay, and that happens to be proportional to square root of t, where t is the time. Okay, so that basically is just an indication that the interface moves, diffusively. So whenever there is something that diffuses out, you expect things to slow down with time. Okay, so that's how this is. It always shows a root t behavior. So this is nothing but the fact that this entire heat transfer process is diffusion dominated, meaning conduction dominated, and therefore the length of the melt essentially grows as square root of t. So these are the two insights that you get when you solve the governing equation. Are there any questions so far? If you have something, you could also type it in the chat box. I'll take a look. Okay, so now if that's the case, okay, so I showed you the temperature profile. So the temperature plotted as a function of Z at various times. Okay, now I realize that, I probably don't need to do it because I only have a single variable to worry about, which I define it as Z divided by root T as eta, and therefore I should be able to calculate or tell what is the temperature only as a function of eta. And that's what is plotted on the right hand side, x-axis being eta, y-axis being temperature. And when I convert z into z by root t, then you can see that all these profiles collapse to give you a single line, okay, or a single plot. So this entire single line tells you about the temperature, okay, everywhere in the domain and at all times. So that's what this is what this called the self-similar profile. Okay. Now, you could also look at the distance at which the interface is located. So that's what is plotted here. So this is the distance at which the interface, the melt solid interface, is located as a function of time. So you start from the left boundary, which is 0, and as time proceeds, the boundary continues to move, and you can see that it continues to increase like a parabola. Okay, so that's what the conduction dominator problems will always tell you. If you calculate the slope of this curve at every time, which is nothing but dz by dt, that tells me the velocity with which the interface will move. So here is that slope dz by dt as a function of time, and you can see that the dz by dt continuously decreases. So that means that the velocity of the interface continuously reduces in time, but it never reaches a constant. So that means that the problem never becomes a steady, it does not have a steady state solution. It continues to move forever. Okay, so that's the solution of this particular problem, and is a nice problem. So this is the case when you have a stationary heat source. Okay, now the actual problem that we wanted to, okay, so before coming to the actual problem, let me also tell you how this thing nicely comes out if you were to not solve it analytically, okay, but you just do a simple dimensional analysis, because this is a very simple problem with, you have temperature, okay, you have the melting point, you have the temperature that you have imposed on the left surface as the variables. You also have the distance, the time, the thermal diffusivity, the latent heat, and the specific heat as different variables. So to write down a simple, to do a simple dimensional analysis, you could say that one of the variable is a function of all other variables. So you can see that there are like 2, 4, 6 of them. Okay. And you look at the number of dimensions and use the Buckingham Pi theorem. You end up by saying that there is going to be 3 non-dimensional groups. Okay. And the 3 non-dimensional groups, one of them turns out to be ratio of temperatures. Another one turns out to be ratio of latent heat to the specific heat, and the third non-dimensional group that comes out to be again z by root t. Okay, the self-similarity variable. So the similarity variable already comes out even from this simple non-dimensional analysis without really worrying about the details of the problem, and I think that's very nice of this problem. So now we can ask the same question. If you introduce a heat source which is moving, what happens? Okay. So to do that, what we have done is that we have now expanded the unsteady heat balance. Okay, the unsteady heat balance, the time dependent part, the conduction part, and now we introduce this heat source. Okay, the heat source is of strength q dot, saying that that's the rate at which you are pumping heat into the system, times a delta function. The reason we are introducing it as a delta function is to say that, okay, my heat source is a point source. I'm only heating at a point, not over a wide region, to make the analysis simpler. Okay, and I have written it as a delta function of z minus vt, and as you know, the delta function becomes non-zero only when the argument z minus vt becomes 0. Okay, and therefore z minus vt becomes 0 at various points as time proceeds, which is equivalent to having the heat source that is moving in the melt. Okay, now you can see that I have taken away the temperature or the heating on the left side. So if I write down the number of variables, I have lost one variable on the left side, but I have introduced 2 more variables. One is the amount of heat that I am inputting through the source. Second is the velocity with which I am moving the heat source. So I could again do a simple dimensional analysis, and because I have now got one extra variable, I will have one more non-dimensional group coming into the picture. So again, when I look at it, what happens is that the ratio of temperatures comes out to be a function of 3 non-dimensional groups. In particular, I should see that out of that, there are 2 non-dimensional groups which have now separated time and z dependency. So earlier we had just one variable in which z and t came together. Now they have separated out to give two different variables. Okay, which means that the self similarity of the solution that I spoke about earlier when the heat source was not moving, that is lost now. You don't have a self-similar solution anymore. You are actually going to have a different solution where time and length have separated out. So we could look at uh, how does one solve it. So analytically it's a bit hard to do the unsteady problem. So what we have done is we first solved it numerically. So let me tell you a little bit about how one can solve the equation numerically. So remember, this is the equation, unsteady equation that we have along with the heat source, and we want to solve this. So we want to do it in a simple 1D case. So you have this 1D domain as I have shown with this black arrow. We divide it into essentially several parts, each of length delta z. Okay, and then what we have also is the heat source and then the interface of the melt and the solid. Okay, now you have to carefully do few things. One is that how do you impose a delta function in numerical approach? Okay, because delta function by definition is defined only at a point, while when you're solving it numerically, you define temperature only at the grid points. So we convert the delta function into a narrow Gaussian. Okay, we say that the delta function is not really a delta function, it is a Gaussian of form exponential of minus z square. So that way we basically simplify and this term on the last term on the unsteady in the unsteady heat balance. Now you have the first term, which is the second derivative of temperature. What we do is we write it down like this. Basically what I have done is we have taken that second derivative, apply the central difference scheme and just simplify this. Okay, so that this entire equation can now be written down as you see here. Okay, so you have dTA by dt, the d square t by dz square now is a function of temperature at various points. The delta function is just written as a Gaussian function. So you have converted now this partial differential equation, which was in z, into an ordinary differential equation because the z derivatives have gone. But on the other hand, you have also increased the number of equations because this equation, which was valid at every grid point, is written down now. Okay, so the single PDE is now has become into n ordinary differential equations, which is valid at every point in the grid. But that's okay because solving the PDEs are much harder, but while solving ODEs one could still do it, except that you have to solve n of them simultaneously. Okay, so you can solve these n ordinary differential equations simultaneously and calculate temperature at every point. Okay, and that's what we do, except that there is one catch, and the catch is that there is also a interface, right? And at that interface this unsteady equation is not valid because there is a latent heat associated with the phase transition there, and therefore you need to account for that, and the way to account for that is to use the Stefan's boundary condition as I was telling you earlier. So what we do is that we say that, okay, I have this interface, okay, which is basically zoomed into this region here. So I have the interface and I have few grid points around it. I will do a interpolation technique here. Okay, I'll do an interpolation technique to tell me what is the temperature around this point. The reason I want to do it is because I know the temperature exactly on this blue line. That has to be the phase transition temperature or the melting point in this case. So at this particular location, I will know the temperature. I will also know the temperature at the grid points, and therefore I'll write down a local interpolation expression for temperature and substitute in the Stefan's boundary condition. Now, Stefan's boundary condition also includes the velocity of the interface. So therefore, what comes out is that the Stefan's boundary condition simplifies into the velocity of the interface. So instead of knowing the interface position itself, Stefan's boundary condition tell you what will be the velocity of the interface. but that is okay. The velocity of the interface is nothing but dz by dt. That's just one another differential equation that we have gotten to the already we have gotten n differential equations. Okay, so you basically have n plus 1 ordinary differential equations which are to be simultaneously solved. Okay, we solve them. So we solve them and this is what we get. So let me explain to you that. So on the x-axis again I have the length, okay, of the domain. On the y-axis I have the temperature. So you start by putting this heat source, the red color, on the left side. So suddenly you have the solid that's gonna melt and the interface moves. So you start with a step function. Okay, as time proceeds, you see that the temperature increases, reaches a maximum, then goes down, and that continues for a while. But at later times, you see that the temperature increases continuously, then it plateaus out, okay, and then it comes down, and then it becomes zero again. In fact, what is happening is that this particular point, okay, each of these points where you see the sudden decrease, this is where actually the heat source will be located. What that means is that if this was the instantaneous picture, if I look at the temperature will increase from the left boundary, okay, then it will become a constant, a plateau, then suddenly at the heat source, it will start decreasing and then it will reach zero and then it becomes zero in the solid. Okay, and this continues to be the case whenever the source moves, the entire profile moves to the right. Okay, so that is the solution that comes out. So of course, because we are solving a PDE, that means I need to know what is the boundary condition on the left side. I need to know what is the boundary condition on the right side and so on. And therefore, we have done it for like various cases. For example, on the left hand side, we have imposed a constant temperature, which is nothing but the Dirichlet boundary condition. On the left hand side, we have imposed a constant heat flux boundary condition, the Neumann boundary condition. We have also changed the way heat is imposed into the system. So instead of prescribing a constant heat flux, you prescribe a constant temperature. So irrespective of whatever you do, you always see that there exists a horizontal or a plateau, and then there is a reduction, more like an exponential. Okay, irrespective of any case that you do, you can see this much clearly in this plot, where what is plotted is in a different coordinate system. Okay, so what you do is that you take the same system and instead of plotting it at with a prescribed z, you define an z, or you define a coordinate system that is moving with the source. So if I am moving with the source, what is the kind of profile that I see? So the left side plot that you're seeing here is nothing but the temperature that I see behind the source. So you can see that initially there was some increase. So this is the way time increases in this plot. What you see is that there is always a constant behind the source, and the region in which the constant temperature is the solution that increases with increase in time. On the other hand, this plot, okay, the right hand side plot is the temperature that is between the source and the interface, the sandwiched region. Okay, and here you see that the temperature always decreases from the source to the interface. Moreover, you don't see any colors here, and that's because all the colors are getting overlapped. Okay, that means the temperature profile between the source and the interface is becoming a constant, or rather the system is reaching a steady state solution. Okay, so if you are moving with the heat source, you see that you are actually reaching a steady state solution with a constant temperature behind and in front, more like an exponential decay. And that turns out to be the solution, which is very different from the self-similar solution that we had when the heat source was stationary. Okay, in other words, the stationary heat source gave us a self-similar solution, but the moment you move it, you basically get into a different solution, which is a steady state solution. You can actually see how does the whole thing come about. Okay, so here what is plotted is the time on x-axis and the velocity of the interface on y-axis. Okay, so we can follow one of the curves, let's say. So you start, when you start, the heat, the source will be on the left hand side, okay, and everywhere it will be solid. So that means that the solid is going to immediately melt. The velocity will be very large, but with time the velocity of the interface will become smaller and smaller. So we saw that earlier. So just as we saw earlier, the velocity of the interface continuously comes down. Okay, if the heat source was not moving, this would have continued to go down forever. But what happens is that when this comes down, at some point the velocity of the interface becomes equal to the velocity of the heat source. Once they become equal, then the velocity of the interface doesn't change anymore. You can see that once the velocity becomes reduces and then becomes equal to this dash line, where the dash line actually corresponds to the velocity of the heat source, it becomes a constant and it stays there. So that is as if the heat source is moving to the right, and that heat source will continuously push this interface to the right, but with the same velocity. And when two things are moving with the same velocity, the distance between them cannot change. Okay, and therefore that continues to be a steady state solution. So that's what happens, and that is how the system reaches the steady state. Okay, you can also see that there are different curves that I have plotted. They correspond to different amount of heat that you are giving. So as you go from blue to red, so blue to red, you are giving more and more heat into the system. Okay, so when you are giving more and more heat into the system, initially the velocity of the interface will be larger, you're seeing here, but all of them finally reach the same velocity as that of the heat source. So this phenomena of the interface that is moving along with the velocity of the heat source, irrespective of the amount of heat that you give, is again a common thing. Okay, or a universal thing of this system. And here what is plotted is z0 minus zs, basically the distance between the source and the interface. So this distance is plotted as a function of time, and you can see that initially they will be very close to each other. Okay, and with time it will increase and then it will reach a constant, saying that it has reached a steady state solution. You can also see that this is for these colors are for various amounts of heat that you give, blue being the smallest and red being the largest. So as you give more and more heat into the system, the distance between the source and the interface gets larger and larger. In other words, when the source is giving you a lot of heat, what it will do is it will push the interface further, but the velocity with which the interface moves will still be same as that of the heat source. Okay, so that's what the numerical solution gives. You will just briefly tell you what the analytical solution looks like, and then stop there. So so now that we have understood that there exists a steady state solution, you could actually look at the analytical and the steady state will exist only if you are moving with a velocity that is with the source, right? So you could actually define a coordinate system which is moving with the source, okay, and convert this unsteady equation into another equation, which is what is given here. So basically you change the z, okay, into a new variable which is moving with the source, and then it changes. So you can see that there exists an extra term which is like v dt by dz. So this is like the substantial derivative that you have when you are moving with a system along with the its velocity. Instead of a simple time derivative, you will have a substantial derivative. So that's what actually has happened here. So that second term appears on the right hand side along with the unsteady term and the conduction term, and this equation has a steady solution, which means I can throw away my left hand side, and that will leave me with a simple second order ordinary differential equation, okay, which can be solved very easily. And we have solved it, and basically you will see that it has got two solutions, one being a constant and other being an exponential profile. It turns out that the constant is a solution to the left of the heat source and exponential profile is the solution to the right side. So you can write down all the boundary conditions and find out all the constants, and we find that the constant temperature is basically expressible in terms of the heat source and other properties, while the temperature profile between the heat source and the moving interface is an exponential profile. You could also calculate what is the distance between the source and the interface. Okay, you can precisely calculate that. So remember, this is what we set out for. I was giving you the simple problem, a 1D problem in which I have a single material and I am using a heat source which is moving with a particular velocity, and I want to know what is the temperature profile everywhere, what is the distance between the source and the melting boundary, and I have now gotten the solution to both the problems. Okay, so this is what I wanted to talk to you. So remember, when I actually started talking about this whole thing happening in a polymer, okay, which may not have a well-defined melting point. So therefore, these calculations need to take another step where you have to tell how much of the polymer is crystallizing. Okay, and in fact, we have done that, but I'll not to you about that. I think it's a good idea to probably stop and take questions. So I'll just say that the oops, sorry. That so that when you have a constant when you have a stationary heat source, you get a self-similar solution for the unsteady profile. But the moment the heat source is moving, okay, because you are imposing a velocity into the system, and then the system responds by gaining the same velocity, and the interface moves with the same velocity, and you can see that this phenomenon remains almost similar even in the case of polymers, which I didn't of course talk about. So I'll stop there, and I'll thank you for your patience. I should acknowledge several people because this has been done in collaboration with Sanat's group at Columbia University. So Sabin is a postdoc there. Ahana is at IIT Madras doing her PhD, and Alexander and Christopher are again associated with this work at Columbia. So thanks once again, and I would be happy to take any questions that you may have.
Audience, if you have some question, you may post here in the chat box. I think nobody is having any doubt regarding the topic. That is fine.
Yeah, you are free to email me about this, or in general, I guess you'll be able to see the email address on the website.
All right, fine. So, Dr. Manilal, you may please have your vote of thanks session. Dr. Manilal?
Yeah, I think online it's quite hard, right? Lot of hiccups. Yeah, Pradeep has a question, and he's asking whether I have used explicit method for time derivative. Yeah, we have done we used the Runge-Kutta method for the integration, which is an explicit method, but it is a stable method. But I think when we started out, we used a very simple scheme, the Euler scheme, and it was still converging. but to be more accurate with the solutions, especially when we wanted to compare with the analytical solution, we moved on to use RK4 Rungakuta fourth order method. But the crucial point, I think, is you should be very careful about the way you track the interface. And that equation, I mean, the solution essentially depends upon the accuracy of how good your integration scheme is with respect to the interface translation rather than the temperature evolution. I hope that answers your question, Pradeep. Yeah, so Krishnadev, I used alpha to indicate the thermal diffusivity, right? The thermal conductivity divided by the density and the specific heat. Okay, so that's like a diffusion coefficient, and that tells you how fast the temperature diffuses in the problem. Like you heat on one side, it's getting conducted, okay, and the thermal diffusivity is the right quantity, which you, if you remember, it will have the units of meter square per second. Okay, so that's like a velocity but with a extra length dimension, and therefore the interface continuously moves, okay, or the heat moves. And so thermal diffusivity tells you that alpha was that. Delta I used to indicate the delta function, which means the where I am heating the the material, because I didn't want to heat it over a longer range. I wanted to heat it only at a particular point. So that point, so if you want to do something at a particular point, you rather use a delta function. So I have used delta to indicate that the heat source. So I hope that clarifies Krishnadev's question.
And Dr. Pradeep is having yet another question, I think.
The standard deviation for Gaussian. So the analytical solution was for a delta function. So we wanted to keep the standard deviation as small as possible. So ideally 0, which means we would come back to the delta function. But since we are solving it numerically, we have a small length scale in the problem, which will be the delta x, the discrete length. So we chose the width of the Gaussian to be greater than delta x, but still much smaller than the total domain size. Okay, so that when you look at it from the perspective of the entire domain, the Gaussian looks smaller. Okay, but the width is still sufficient that there are few grid points. So that determines the standard deviation for the Gaussian. So I hope that answers your question, Pradeep.
So that's fine. So I think Dr. Manilal could not join. I think this having some technical issues are there.
No problem.
So I myself, Dr. Ramachandran, Professor Government Engineering College Thrissur, one of the conveners of icetest 2020. So on behalf of the organizing committee and rampts 2020, on behalf of all the delegates, I thank you, Dr. Sumesh Thampi, IIT Madras, Department of Chemical Engineering, for this enlightening presentation on directional phase change induced by a heat source. I think it is quite new to many. So I think it will be informative, and definitely it will trigger the chance for doing some research in that area for many of the audience. So I thank you once again for having been accepted our invitation and present here to in fact enlighten the audience with your lecture. Thank you very much.
Thank you, Dr. Ramachandran. Okay, see you.
All right, fine. So we will start our first session of the conference, sub-conference RAMPS 2020, with the presentation by Professor Manoj PJ of GEC Thrissur. And the chairs are in fact Dr. Jidesh from Government Engineering College, Kozhikode, and the internal chair is Dr. Sunil A.S. from GEC Thrissur. So I think they are ready to join. So you, all of you, may please wait for a while.
Recent developments in ejector
Hello. Hello.
Okay.
ലാബിലാണ് ഇപ്പൊ എനിക്ക് ഇൻവിറ്റേഷൻ വന്നു, ഞാൻ അക്സെപ്റ്റ് ചെയ്തു.
Okay. Now fine only. ഇപ്പൊ കേൾക്കാം, കുഴപ്പമില്ല.
ഉണ്ട്.
Jidesh?
Sir.
So we will start, ready alle?
Yeah, we can start, yeah.
Okay, fine. Thank you very much for joining. So this session is going to be chaired by Dr. Jidesh PK from Government Engineering College, Calicut. So we will begin the section with the presentation of Mr. Manoj PJ.
Refrigeration system. Presented by Manoj PJ, Government Engineering College, Thrissur. Introduction. Ejector refrigeration system is one of the important methods of refrigeration. It utilizes heat energy as input. ERS is also known as steam jet refrigeration because high pressure, high temperature steam is commonly used in industries as burning fuel. Household applications of ERS are limited because ERS is bulky, non-availability of heat energy, and low coefficient of performance. Major components of ERS: there is a generator, create high pressure vapor using heat energy. Ejector expands the high pressure vapor to low pressure. Evaporator, there will be evaporation of secondary fluids, leads to the refrigeration effect. Condenser condenses the vapor to liquid, and pump is used to pump working fluid from condenser to generator, and throttle valve is used to reduce the pressure and supplying the makeup fluid to evaporator. Basics of ejector refrigeration system. The heart of the refrigeration system, ERS, is a ejector. Ejector basically consists of a nozzle through which the primary fluids expanded to low pressure. There is a chamber. Chamber is having three parts. One is the suction chamber, constant area section, and diffuser part. And there is an opening for secondary fluid because as the primary fluids expands to low pressure, creates a low pressure environment, leads to evaporation of secondary fluids. That vaporized secondary fluids is drawn, or it is sucked by the primary fluids as indicated in the green mark, that will move along the constant area to the condenser. Usually the primary flow will be choked at the throat section of the nozzle. That means the velocity is maintained sonic velocity. This primary fluid will create a fictitious flow path as indicated in the red line, and leaving an annular space for secondary fluids. By adjusting this particular velocity of the fluids and geometric factors, it is possible to create a sonic velocity for secondary fluids at these particular sections. Such a situation is known as double choking mode. That means primary flow will be choked at the throat and secondary fluids will be choked at this particular point. A mixing of primary fluids and secondary fluids takes place from section YY to section MM. Further mixing takes place as it moves to the condenser side, and there will be some dynamic shocks are observed at this particular section YY that will pressurize the secondary fluids. So these particular arrangements can be used to work as a pump also. Here the refrigeration effect is due to the evaporation of secondary fluids. Objective of the study is to review the recent developments in ERS. Categorization of research in ERS. Improving the performance ERS by varying the working fluids. Improving the performance by geometric modification of different components of ERS. Make the ERS environment friendly by utilizing the green energy source, design modification of ERS to eliminate moving components like pump and throttle, numerical and experimental results. Performance analysis of ERS with varying the operating modes of ejector. The ejector can work in 3 different modes. One is the critical mode, subcritical mode and backflow mode. In critical mode, there will be double choking as I already mentioned. In subcritical mode, only single choking takes place for the primary fluid. Backflow mode is a malfunctioning mode. The graph is shown between entrainment ratio versus condenser pressure. Entrainment ratio is the ratio of mass rate of evaporation of secondary fluids to mass flow rate of primary fluids. It is found that the ejector is maximum efficient when it works in critical mode or in double choking mode. Another factor is the geometric parameters. One is the nozzle exit position. It is marked as X. Nozzle exit position can be maintained at suction chamber or it can be extended to constant area section. The position of the nozzle exit is also affects the performance of the ejector. It is found that performance analysis of ERS by varying the geometric parameters. Moving the nozzle exit into mixing chamber that is nearer to the constant area section reduced COP and cooling capacity of ERS. Effect of compression ratio and expansion ratio on the performance of ERS. Expansion ratio is the ratio of generator pressure to evaporator pressure. Compression ratio is the ratio of condenser pressure to evaporator pressure. COP increased with increase in expansion ratio and decreased with compression ratio. Performance of analysis of modified ERS without pump. In this particular diagram, you can see an ordinary ejector. The pump is eliminated by introducing a secondary ejector. A small quantity of vapor is utilized for the secondary ejector and that will work as a pump that is utilized to pump fluid from condenser to generator. Another method used is placing the different components at different heights. That we can eliminate the pump as well as throttle. Performance analysis of ERS with solar energy input. Here there is a solar collector and there is a storage tank. Solar energy may not be available throughout the day, so there is a solar storage tank is provided and there is a pump to recirculate this particular fluid to collect the solar energy. And other part is the normal ERS systems. Another modification is also done by providing one more storage tank at the evaporator site. So the cold secondary fluids can store in this evaporator also. Performance analysis of ERS with different working fluids. Researchers tried with various refrigerant like R142B, 134A, 152A, R600A having low ozone depletion potential and low global warming potential. This makes the system suitable to utilize low grade thermal energy like solar energy input. With 142B ejector with fixed dimensions, researchers predicted a condenser pressure of 0.46 megapascal and entrainment ratio of 0.4. With 134A, reported that maximum entrainment ratio is 0.35 and at generator temperature of 80 degrees centigrade got COP of 0.25. With 600A, maintain the evaporator temperature of 10 degrees centigrade and condenser temperature of 36 degrees centigrade, boiler pressure of 120 degrees centigrade and obtain COP of 0.089. Conclusions. Plenty of research works have been carried out in the field of ERS. Both numerical and experimental studies were carried out with variety of working fluids and geometric design modifications. All this research revealed that there is a large scope of improving utility of ERS with low temperature renewable heat energy input by selecting suitable working fluids with zero depletion potential and low global warming potential along with renewable energy input source like solar energy will make the ERS totally environment friendly refrigeration method. Most of the numerical studies were conducted with ANSYS fluent software. The results obtained with the software are very much close to the experimental results. Most of the studies were conducted assuming steady state conditions of generator and condenser temperature, but in practical situation, generator condenser pressure may vary. So this requires transient boundary conditions in this analysis, but such analysis are found very less. Even though there is a different studies conducted with the to improve the COP of ERS, maximum reported COP falls below 0.4 only, whereas the vapor compression refrigeration system gives COP above 3.5. But COP alone cannot be taken a criterion for comparison of ERS because ERS use low-grade thermal energy for refrigeration. ERS is a very live area of research and it will emerge as a common method of refrigeration not only in industries but also in household applications. So these are my reference. Thank you for your kind attention.
Professor Manoj, that was am I audible?
Yes, yes.
That was a nice presentation. I have one or two questions. You mentioned that we can use different types of refrigerants, but usually ejector refrigeration system is common with steam jet refrigeration. So, is there? How do you relate both? It is a very common technique with steam, but with other refrigerants, how this is possible?
Yeah, it is commonly used as steam as refrigerant. In olden days, steam was very commonly used in industry. But to produce steam, industries may have a lot of waste heat. But to make use low grade energy, means if you want to use solar energy, it will not be possible to give that much heat input. So, to make use of low temperature, low pressure generator addition, you may require refrigerant. So that's why the system is trying to modify this type of refrigerant. So by using this type of refrigerant, we can make use of solar energy. Otherwise, it is not possible.
Can you give some examples of refrigerants?
For example, if you can use 134A or 600A, as I mentioned, you can maintain low temperature generator. With that particular low temperature, you can produce refrigeration effect. If you are using steam or water as a working fluid, if you want to make steam, you require very high temperature. So that much temperature may not be possible with solar energy. So by changing this particular refrigerants, which you can make use of low temperature generator. With that low temperature, you can generate vapor. That's the use of this particular low temperature refrigerants.
Okay, one more question. Like you are mentioning shock waves. So this is actually when we are trying for low grade or low intensity waste heat. Uh, Whether that kind of supersonic velocity will be there to create a shock wave inside the.
As I already mentioned, if you are using ejector as a pump, then production is very important. You want to create very high pressure. But if you want to make use of this particular ejector as a refrigerant, our aim is to make refrigerant more evaporation, not to make shock wave or produce very high pressure. So in this case, our aim is to focus produce refrigeration effect. Where the shock waves are not important.
Okay, Dr. Sunil, are you asking any questions?
Yes, you have told there are so many refrigerants are possible. So which one you are preferring for an ideal fluid for this ERS?
Actually, they tried with a lot of refrigerants. Out of that, maximum efficiency means enrichment ratio. As you consider this system for generating refrigeration effect, 134A gives the better results, almost equal to zero point 0.4 COP. All other refrigerants give lesser than that. Or enrichment ratio is also less. So, if you want to make the use of the system for refrigeration effect, R134A is found better.
Okay, I think this one is a review analysis. Okay, so what is the scope of doing an further investigation on this particular subject?
There are variety of refrigerants, new refrigerants available, hydrocarbons available. So it is not tried with this type of new refrigerants like 32 R32. So and also with a lot of hydrocarbons are coming, hydrocarbon refrigerants are coming. So the experiments are not conducted in this particular refrigerants. Also, as I already mentioned, transient conditions are not analyzed. So transient conditions can be analyzed, and there are so many other new refrigerants where the experiments are not tried with the particular new type of refrigerants. So it is possible to try this particular refrigerants for this making this ERS better performance.
So during the selection of these types of refrigerants,
In the
the
chat box,
environmental impact is a major concern. So what about those issues? So how whether this one is advisable to reduce the environmental impacts? This
First of
type of
all, we are
refrigerant.
selecting environment friendly refrigerants, basically hydrocarbons. It's having zero ozone depletion potential, zero global warming potential. So we are trying with environment friendly refrigerants. Also, the systems can be modified to include solar energy. Thereby, the ERS system can be completely environment friendly. It is possible to make the system totally environment friendly. So that is the scope of this ERS.
Okay, now there is a question from the audience that is, I think it is not within the purview of this presentation. May I know what are the transient boundary conditions? It is something related to heat transfer, I think. Or I think it's not related to this area. I think we can skip off it,
no,
We can.
Professor Manoj actually mentioned something about transient conditions.
Okay, that may be.
Yeah.
Transient conditions are not analyzed because the temperature, input and temperature, suppose we are using solar energy, it is not a steady one. So temperature may vary. Similarly, condenser condition temperature may vary. Such transient conditions are not analyzed. That's what I mentioned.
So what he has mentioned, it is only transient condition, not boundary conditions, in fact. So, okay, I think we have to stick on to the 3 minutes limit, maximum for discussion. So, I think it is fine. So, these chairs may please mark his, grade in the evaluation sheet, and we will move on to the next presentation. So, if you want to wind up, you can within maybe few.
We'll move on to next
Okay,
presentation.
fine. So, all right, fine. So, okay. So the next presentation is by Mr. Rahul CG, and the presentation title is the design of gas cleaning unit for biomass gasifier.
Good morning, everyone. My name is Rahul CG. I am a M.Tech graduate from GEC Calicut. Today, I am here to do a presentation on the topic Design of Gas Clean System for Biomass Gasification. Going towards the first slide, there is introduction. As we know, gasification is a process of thermal conversion of biomass into a combustible gas mixture through the process of incomplete combustion. The gas mixture that is produced from the gasification mainly consists of hydrogen, carbon monoxide, carbon dioxide, methane, and other gaseous materials, along with the impurities such as nitrogen, sulfates, chlorides, and water vapors, tar, and other particulates. Here, the objective is to remove these impurities such that the clean syngas produced can be supplied to other systems such as fuel cells or IC engines for the production of energy. For this process, for the gasification process mainly, there are three types of gasifiers that are currently being used. Those are updraft gasifier, downdraft gasifier, and cross-draft gasifiers. These gasifiers are mainly used for the gasification process. Now going for the next slide. Objective. Here the objective is to design a gas cleaning unit to remove impurities such as tar, HCl, nitrogen compounds, alkali compounds, and then supply is the main objective, and then the gas can be supplied for other systems for the energy production. Next is the methodology. First one is the gasifier selection. Here I have selected the downdraft gasifier for the gasification process because it's mainly because of the reason that comparing the all three gasifier systems, the downdraft gasifier produces very less amount of impurities comparing the other two systems. That is a major reason for selecting the downdraft gasifier. Next is the design of the gas cleaning unit. Here I have selected the design of the exhaust pipe of a Royal Enfield Bullet. This is the main design of the gas cleaning unit. The syngas that is produced from the gasification process is applied towards the so-called proposed cleaning unit, and the cleaning process takes place. The simulation of those two is done with the help of ANSYS software. This is a literature survey. Due to the time constraint, I'm not explaining everything in detail. Just give you a small glimpse of these journals. From the first journal, I was able to conclude that major impurities that are produced from the gasification process are harmful for the fuel cell. So it's one of the major reasons for removing these impurities from the syngas produced. Next is the numerical investigation of the wood chip downdraft gasifier. This is one of the most important journal because I have used this journal as the for the validation process. Here the two ANSYS analysis was done with the help by using the wood chips as the biomass inlet, and I have used this journal paper as the validation for the validation of the gasifier. Next, in the third journal, I was mainly able to conclude that the biomass gasification product gas can be cleaned to meet the requirements for the use of SOFCs, that is solid oxide fuel cells, with different possible system schemes applying different possible lower temperature to the gas cleaning system. Next is showing about the determination of calorific values of the coconut shell and coconut husk. From this journal, I was able to conclude that the use of coconut husk and coconut shells. This journal suggested that the coconut shells can be used in place of firewood for energy generation and cloth drying. Next journal is mainly used as a reference for the designing and the simulation work of the exhaust pipe for the gas cleaning system. Now going forward towards the summary. Here, different biomass inputs are available and the appropriate input is needed to be selected for the simulation process. It was later decided to use the coconut husk as the input. One of the major reasons for selecting coconut is it gives the highest output of hydrogen and carbon monoxide among the biogas resources when the gasify input flow rate is kept constant. This is one of the major reasons for selecting the hydrogen and for reason selecting the coconut husk or shells as the biomass input. Next is the use of metal oxide along with activated carbon on the cleaning unit for removing the impurities that are produced from the syngas. These are the impurities that are produced during the gasification process. Mainly those are the carbonaceous species, the chlorine compounds, and the sulfur species and the nitrogen species. These are mainly found in the gaseous state, and next that is mainly found are the particulates which is in form of carbon compounds. Next is tar, which is generally in liquid state. Now going for the next slide. This is the small flow chart showing the process that has been done in this presentation. I mean, in this experiment. First one is the coconut husk is used as the feed to the gasifier. Then the syngas production takes place. Then they supplying the syngas that is produced to the proposed cleaning unit. Then the removal of impurities with the help of metal oxides such as ferric oxide or potassium carbonate with the help of also with activated carbon. Next is the cleaned output gas as the cleaned input syngas. Next is the simulation of the downdraft gasifier. Here the three assumptions are taken for the effective working. First one is the 3D steady state. Next is the incompressible flow, and next is the adiabatic wall condition for the combustion zone. This is the energy balance equations. First one is the continuity equation. Second one is the energy equation. The third one is regarding the momentum equation. Going to the next slide. This is the geometric model of the downdraft gasifier. As you can see, the geometry is about 481 millimeter and it's 178 millimeter in width. This is flow pattern that takes place in the downdraft gasifier. That is, the biomass with air is supplied from the top of the system, along with the air that is being supplied to the pyrolysis zone. This is the pyrolysis zone for the gasification process, and the clean produced syngas is sent from downwards. This is the grid-dependent study of the downdraft gasifier. The optimum value was taken as 22,59,831. Next is the material properties. These are the four material properties that are mainly used for the simulation work. That is the properties of air, the properties of stainless steel, the properties of biomass. Here I have selected the biomass as the coconut husk. These are the properties of the biomass, properties of the coconut husk. And next is the properties of ceramic wool. The ceramic wool is mainly used in the gas cleaning system. Next is the equivalence ratio. The equivalence ratio is defined as the ratio of air fuel rate of, it's defined as the ratio of mass flow rate of air fuel mixture to that of the air. Here for carrying out to finding out the optimum gasification point, here four values are selected for an analysis has been done on these 4 points. That is 0.19, 0.26, 0.33 and 0.4. Here the mass flow rate value of the feedstock is set at 0.011 kg per second for all the 4 simulations, while the air flow rate changes according to the equivalence ratio. As the value of the equivalence ratio increases, the oxidation temperature also increases due to the amount of oxygen concentration in the oxidation zone. The jar combustion and the volatile reactions are also triggered, and as a result, the temperature increases. But at a certain point, when the ER value increases, there is a significant drop in the temperature, the pyrolysis zone. And the drying and the pyrolysis zone takes heat from the oxidation zone, and therefore this process is linked with the endothermic drying, pyrolysis zone, and an exothermic oxidation zone. So it's an optimum value is needed to be selected from a point where there is a temperature drop and the temperature rise is balanced, and the process takes place very effectively. Next, we are taking the first 2 points, that is the equivalence ratio 0.19 and equivalence ratio 0.26. As you can see in the first case and second case, in the first case there is a large amount of heat is being dissipated near to the pyrolysis zone. As you can see, the maximum temperature is around 1705 and the amount of temperature dissipated flows towards the top of the system. While in the second case, as you can see, the human distribution of the temperature is much comparatively less compared to the first case. But the pyrolysis temperature zone temperature value is almost similar from the graph, but the temperature dissipation is comparatively low. From the third and the fourth case, as you can see, the equivalence ratio is increased from 0.33 and 0.4. You can see that the dissipation is very low in the last two cases. As you can see in the third and fourth diagram, only the combustion zone only has the temperature, rest the temperature there is a very low decrease. So from these four figures, we are able to conclude from these four temperature distribution, we are able to conclude that the equivalence ratio, second case, that is equivalence ratio of 0.26 is the optimum case from the four cases that are taken. As you can see, there is optimum. As you can see from the temperature distribution, the equivalence ratio 0.26 shows the equivalent temperature variation comparing to all the other three. In the first case, there is a large increase in the temperature, whereas in the second case, final case, third and the fourth case, there is not much of an increase in the temperature. So the optimum case is taken as the equivalence ratio 0.26. This is the result analysis of the gasifier for the equivalence ratio of 0.26. Here the maximum temperature, the outlet temperature from the gasifier is taken to be as 1285.7 Kelvin. This is the temperature distribution curve. As I had seen earlier, the input temperature is 300 Kelvin, the output temperature is 1285.7 Kelvin. Next is the validation simulation. Here the validation of the gasifier model has been done with the help of numerical investigation of wood chip gasifier. In this journal, the simulation is done based upon the wooden chips. So for the validation process, the biomass inlet is considered as the wooden chips and the simulation is done. From the temperature distribution graph, it is found out that the temperature produced is very similar to that of the temperature distribution of the journal. This is the validation journal graph that has been plotted. As you can see, there is a very small difference in temperature after the graph is being plotted. The first case is about the journal and second is the simulated journal. Now going to the next slide. Next is the simulation of the proposed cleaning unit. Here the main three assumptions taken are 3D steady state, incompressible flow and adiabatic wall condition of the combustion zone. This is the schematic diagram. Here there are mainly three important parts. First one is the outer metal sheet cover. It's mainly of stainless steel. Next is the perforated tube inside the metal sheet cover, and next is a ceramic wool which is used as insulator. This is the geometric model of the proposed cleaning unit. The length is 101 mm and it's 8 mm width. This is the grid dependent study. There's nothing much in detail to be explained here. The optimum value is taken as 2651. Next is the resultant analysis of the proposed cleaning unit. Here the inlet temperature of the proposed cleaning unit is the same as that of the outer temperature of the outlet temperature of the gasifier, that is 1285.7 Kelvin. Here from the simulation work, it is found out that the outlet temperature maximum received is 1264.6 Kelvin. This is the temperature distribution curve. 1265 is the outlet temperature that is being found out. Next is the gas cleaning unit. Here the gas cleaning unit is needed to be fabricated to remove impurities such as its HCl and H2S. Here with the help of using metal oxides such as ferric oxide and potassium carbonate are used to remove these impurities. These metal oxides are mixed along with the activated carbon, which increases the percentage of absorption process. It's mainly because activated carbon has higher absorption rate in the moisture state, and with the help of these metal oxides and activated carbon, the impurities can be removed. Next is the conclusion. From the results, it was concluded that the optimum value of equivalence ratio is 0.26 and the maximum temperature obtained from the simulation is 1365 Kelvin for the downdraft gasifier, and the outlet temperature from the gasifier is found to be 1285.7 Kelvin. The syngas produced is directly supplied to the round-off gasifier to the cleaning unit, and the temperature distribution was found out, and the outlet temperature was found to be 1264.6 Kelvin. These are the references. Thank you.
Okay, Rahul, am I audible?
Yes, audible. Rahul, where is he?
Rahul. So regarding your presentation, you are actually talking about the design of a gas cleaning unit, but I could not see any result regarding to that, whether you are able to clean the producer gas from the gasifier or not. So my first question is regarding the first part of your presentation. How did you take care of the energy source term shown in your energy equation? Was it a constant value, or you modeled it as a reaction?
Rahul, are you there? I think he has lost his connection, I think. He's still in the state of play. He lost his connection, I think.
So what can be done? Shall we wait, or?
No, let us see another 30 seconds or so. So if he's not coming back,
Yeah.
we'll move on to the next one.
Okay.
So I think he's not available. So I think better we'll move on to the next presentation.
Yeah. Okay, sir. Yeah, that will be good.
Okay.
So next one is by Mrs. Miss Ampili PN. So
Hi everyone, myself Ambili PN, research scholar at GEC Thrissur. Today I am very much happy to present my paper on jet mixing enhancement of a supersonic twin jet nozzle using rectangular tabs in this international conference icetest 2020. At this moment, I thank all my co-authors, my guides, and all other people who helped me to complete this paper successfully. Okay, now we can go to our paper. This is our introduction. The increased demand of supersonic and hypersonic vehicles in the field of military and space application promotes the development of nozzles with high performance. All the nozzle performance parameters like thrust, specific impulse, decreased drag rate are highly dependent on the interactions of the exhausted gas emerging from the nozzle exit with the ambient air and the structural components around the immediate vicinity. During the launch, space vehicles are subjected to violent vibroacoustic loads due to the high sound pressure levels and the transient side loads produced during the rocket engine ignition. These loads are known to cause electronic and mechanical component failures as well as produce adverse environmental conditions for the vehicle occupant and payload. In this scenario, a nozzle with high performance parameter with a low noise is highly demanding. The current study focuses on the jet mixing enhancement of a twin jet nozzle. The design expansion Mach number is 1.6 with the vortex generators at the exit. The increased jet mixing leads to the decrease in generation of acoustic loads. These are our objectives. The first objective is to design a twin jet nozzle with the 2 rectangular tabs at the exit plane. And the next one we have to analyze, decided to analyze aerodynamic and acoustic characteristics of the designed model at various conditions by the ANSYS Fluent software. And the last objective is to show that the enhanced jet mixing, which in turn leads to the reduction of noise level. Next is the literature survey. For this one, we collected a lot of papers, and from these we categorized as which related to shock associated noise, which related to vortex generators, twin jets with vortex generators, etc. So from these one, we presented here only four. The first one in 1982, C.K. Tam and H. Tana studied experimentally and theoretically the characteristics of shock-associated noise of the supersonic jet from the CD nozzle. And in the next paper, Arun Kumar P. and E. Radhakrishnan in 2014, they demonstrated the mixing capability of a right-angled triangular tab at the CD nozzle